Hi, welcome back to my YouTube channel, Steve Learning Note. With me is Steve, and I'm going to share my learning note about risk-based authentication's characteristics. Authentications means determining who you are, proving who you are before allowing you to come into the systems. And to prove who you are, we can use with something that you know, like password or PIN, with something that you have, like your mobile device, for example, because let's say the authentication is tied up with your mobile device, and also with something who you are, like fingerprints, biometrics. All of these features, however, has its own limitations or weaknesses. Password, for example, it can be stolen, and then users can use a weak password. Phone can be stolen, and if it's stolen, then the attacker can get that authentications proved. Biometrics also can be fake, or the attacker can use a similar biometrics to trick the sensor. And because of these limitations, usually the system use combinations of these factors. It can be combination of two, or sometimes they use all of the three. I'll give you an example. If you want to get money from the ATM machines, you need to use with something that you have, which is the card, and after entering the card, you need to put your PIN number. That is something that you know. So using more than one factors, also being called by 2FA, two-factor authentications, if there are two factors that are being used, or multi-factor authentications if the system use more than two factors. Improving the security is important for the businesses. So for example, this is the illustrations of the strength and preferred authentications methods in Microsoft Entra ID. You can see that we can improve the security of the authentications from the bad to the good and the better and the best by adding more authentications factors into it. But the problem is that if adding more and more factors to the authentication systems, it can make the system is unusable because users needs to do more steps to do the authentications. So as a business, from the business point of view, improving the security is important, but also improving or making sure the usability of the applications is also important. Therefore, we have to find a balance between security and also usability. And also, it turns out that MFA still have its own weaknesses. For example, it's fatigue attack, or also known by MFA bombing. So basically, the attacker tried to send a lot of login attempts, right, and also send a lot of phishing emails to the users, so that they hope the target will be tired with all of those informations, and they will click at least once that MFA prompt, so that the attacker can get the authentications proved. And it turns out it happens in the recent years in the big companies like Cisco, Uber, and Apple. So is there a way to improve the authentication security without adding additional steps? Yes, there is, which is by adding a risk factor, or usually called by risk-based authentications. Risk-based authentications is an approach to improve account security on websites without forcing users to use 2FA. So it is not specific to the website, but any online services applications too. How does it work? So for example, you are the users, you log in with username and password, and usually to the request, it also send IP address, user agents, device types that you use. And then the system will calculate that with your login histories, and it will produce a risk. So risk can be low, medium, or high. Right? If the risk low means the high trust, the system will allow you to log in. Right? For example, if you log in with the usual IP address, usual user agent, device type, system will know that is you. If the attackers try to log in, but they use different IP address, different user agent, different device type, so that the risk is high, then the applications can reject that login attempt. But what if in between? So if let's say you use your usual device type, usual user agent, but you log in different locations because you are on traveling, then maybe the system will ask you additional steps, which is the terms is step-up authentications. So it's basically a process to challenge you with additional authentications method to prove your identity. And then to calculate those risks, we need to use features. What informations that we can use to calculate or to compute the score of the risk. And we can use with something that you have, something that you are, and then something that you know, and MFA also can be used. Besides that, we can use based on user behavior informations like the time that user usually log in. For example, if you build an applications for your employee and then you are expecting them to log in during the working hours, but then someone tried to log in like in the weekend, for example, and that can increase the risk. And the durations, like how long they use the applications, the failure rate of login attempt before, and then the behavior biometrics. It means that the systems try to learn your way, your behavior, let's say to input a password, right? For example, like if the users input a password like maybe stopping in the middle, right, the behavior is different with usual behavior, then it can also increase the risk score. And based on the context, like device type, right, if you use different device type, it can increase the risk score. Different configurations, if also the user use jailbreak applications or jailbreak a device, it can be a high risk. And also based on geolocations, like incorrect locations, impossible travel, like you are traveling too fast, and then the system thinks it's impossible to travel that fast to different locations, it can increase the risk. And also if the IP that you use, let's say, has been used before by attackers, right, your IP has a bad reputation, so the system also can increase the risk. And also based on the transitions, like the type, value, and sensitivity of the data, which is if the risk is low and sensitivity of the transition is low, we can allow the login. But if the sensitivity is high and the risk is high, then we definitely need to reject the login. But what if the risk is low but sensitivity is high? We can probably still allow that login because the risk is low, even though sensitivity is high. And what if the risk is high and sensitivity of the transaction is low? then we can add you or request you to do additional authentication steps. And RBA is actually recommended by many security agencies across the world, including, like, for example, here, Australian Cyber Security Center, by the White House, also by NISC. But still, not many applications out there use or implement this, probably because they don't know or they don't know how to implement it. So that's why some people out there make a research paper around it to showcase how to calculate the score, how to choose the features, and etc. etc. And I'm going to explain it to you about this research paper conducted by Stefan, Marcus, and Luigi. So what they're trying to do is they trying to find the performance of model to calculate the risk. They use two kind of model. First is simple model. What is simple model? It's basically they try to do exact match with your current login informations against your login histories, and for every match they will count it and divide it by the total number of considered features. So for example, in the example, there's a user, he tries to log in with the same IP address that he has been used before, with device type that he has been used before, but at this time the user agent is different. So the score is calculated by 1 plus 1 is 2 divided by the total number of considered features. In this example is 3. So the score is 0.6. So if the score is more closer to 1, the risk should be like lower. If the score is towards to 0, the risk should be higher. And this simple model is inspired by a single feature model that is being used by open source applications called OpenAM or OpenAM authentications. Right, in the source code of these applications, they also do exact match based on, let's say, IP range check, IP history check, and then for each features, they sum the current score by the features score or features weight. So then they will have the total numbers, and then they will just check the total score by the threshold. And the next model is extend, which is basically they try to check the ratio of probability from the global feature values with that user's legitimate features values, and then multiply it with the probability ratio of the attack attempt with the legitimate login ratio. So let me try to explain the formula. So I'm not a mathematic professional, so so if I interpret this formula wrongly, please correct me, okay? So the first part of the formula, these symbols over here, is basically try to multiply across all features that we are going to compute for K1 until KD. So for example, if we have 3 features like IP address, user agent, and device type, so it will compute this likelihood ratio each for that features, okay? And this part is the global probability, right? So if you log in with a specific IP address, you try to check the probability of the occurrence of that value across all users' login histories. And then the second part is the user-specific probability. It will check the probability of occurrence of that feature value appear in the user's legitimate login history. And this ratio between global and user-specific probability will result a number, and that number, if close to 1, right, it means that the feature value is as common globally as it's for the specific users, meaning it's not unusual. And if the ratio is much greater than 1, it means that this feature value is rare in the user history, right? And then compared to its general occurrence also is rare because of that, like this IP address, for example, like we never seen this before, so that the potential of suspicious login attempt should be higher, right? Meanwhile, if the ratio is close to 1, means that yeah, we have seen this value commonly globally, and also for this specific user, he has been using that also before, right? So it's not unusual. And then the second component of the formula is the attack probability, right? Basically computed by the this one, by this formula. 1 divided by u is the total number of users. Assuming that every users are equally likely to be targeted, right? In the test, right? But if in reality your application has like a VIP customers, maybe this formula need to be changed. And the second part is legitimate login probability, which is computed by dividing number of user logins, legitimate logins, with numbers of all logins. That will result a ratio of attack and legitimate probability. So if the ratio increase the score when the user, this ratio increase the score when the user's legitimate login frequency is low compared to the assumed attack probability, suggesting that an infrequent user login is more suspicious. Yeah, that makes sense, because like if the users log in rarely, like the systems cannot really tell if this is like the legitimate you or not, because it does not have enough data to check, right? So this is the extend model based on the ratio. It's some statistic stuffs. Alright, and before I forget, so you can see the code implementation in this link, which is written in Python. So how about the performance? So there are 3 attackers models that is being used in the research paper. First is naive attackers, where the attackers only know the IP address. He doesn't know the locations of the target, right? But he already knows the credentials. Okay. VPN attackers is naive attackers, but he knows the target's country, so he used VPN to spoof the IP. But he doesn't know the user agent, so he just used the popular user agent string. Targeted attacker, he knows more, so he knows what VPN attackers knows, plus the target locations, and also user agents. And this is the graph. So the first row shows the median re-authentication count per users, right? How many login attempts that it needed before the system prompt another re-authentications. And the second one is the median re-authentication rate, right, per users. And the y-axis is the value, x-axis is login history size. If you see different color, it means the TPR, right? TPR is true positive rate, so it is the percentage of block login attempt that is correctly identifies as attack attempt and is successfully blocked. Okay, so it has different color because of different model configurations and features configurations. Alright, so if you can see from all of these models, which is extend using 2 features and then simple model using IP and user agent features, and simple model also, but using all features. You can see that if the history size is larger, then the count of users need to re-authenticate is higher, which is good, right? And then and also the rate of the users to do re-authentications tends to be lower, which is good. Why? Because again, yeah, the models knows the users better when it knows more data about the login history behavior of the users. And then the light gray line here is the baseline performance of 2FA, and the dark gray line is a stable setup threshold, right? You can see the performance of each model here. And to summarize about that testing over here, right? How often does RBA request for re-authentication in particular deployment? So I will just read it because this is just testing result, okay? So for naive attackers, never ask for re-authentication at all except for simple IP with TPR 99%, which is every 12 time. For VPN attacker, mostly not ask for re-authentications, but there is some cases it will ask for re-authentications. And for targeted attackers, legitimate users were never asked for re-authentications, with TPR lower than 98% in most cases. So I think if you aim for higher TPR, successful rate of blocking, the model will tend to trigger re-authentications to the legitimate users more often. Right? And the second question, how many user sessions need to be captured and stored in the login history to achieve a stable and reliable RBA setup? And the answer is most TPR require one or even no history event entry for blocking the attackers in both models. Storing one entry is sufficient for a stable setup that blocks more than 99.45% of targeted attackers with the extend model. So if you're using extend model, you just need to save at least one entry, and to block more than 99.92%, which is a very high percentage, 10 entries are needed in their cases. So next we are going to check features criteria of choosing features. So the features should have both good levels of stability and at least minimum entropy. I will explain about it later. Be spoofable only with a high amount of effort, and increase differentiations between legitimate users and attackers. So the features can be used to differentiate legitimate users and attackers clearly. So what is entropy? Entropy basically measures disorder or uncertainty in datasets. So if you have datasets, like in this case is login histories, you can check the anomalies, right, or the disorder. So a feature with high entropy is more variable, right, while a feature with low entropy is more predictable or more uniform. I will give you an example later. And spoofable means someone or something disguise itself as a trusted source to gain access to personal information, money, malware, or data, right? So for example, IP address as a feature. So if we use IP address as a feature, and then if we say high entropy IP, so it means that users typically log in from a wide range of IP address, and this variability helps distinguish legitimate users and make it harder for attackers to guess, to spoof the commonly used IP by this user. But if the entropy is low, means that users log in from a few IP address, like for example a company network. They use company network. Okay, many users use the same IP address, so the attackers know this pattern and can spoof or mimic this IP, reducing the effectiveness of IP as distinguished features. Right, that's the IP address example. So to calculate how easy the feature is spoofable, right? How to calculate the entropy? We can use a formula called Shannon Entropy, which is it measures the uncertainty of probability distributions. You can check the detail over here. All right, let me explain it to you. All right, so this part, basically we are trying to check the entropy value of variable x, where x1, right, x1 is a feature like device type, for example, and we are going to sum of each probability of occurrence of the features possible values, right? So for device type features, the possibility value, for example, like desktop, mobile, and tablet, and we are going to check that probability occurrence of these features in the datasets, and then we are going to multiply it with log2 base logarithm, because by multiplying with log2 we will get the number in bits, which is usually used by this kind of case. And we are going to use two kind of entropy. The first one is global entropy based on global login history, right? If the value is more closer to 0, it means it did not contain any information to distinguish between the users. And second, we are going to use user entropy of each feature in the user login history. So if 0 user entropy, it means that the features value occurrence will change, right? They always use the same value in their login histories. And another matrix that can be used to determine this one, differentiations between legitimate user attackers, we can use risk score relations matrix, or RSR. Right, it's a metric to evaluate how well particular features help distinguish between legitimate users and potential attackers. It helps identify which features are most effective at increasing the risk score for attackers while maintaining a lower score for legitimate users. And it computes that by a ratio of average risk score of the attackers with average risk score for legitimate users. Then you will get RSR value. The high RSR value means attackers tend to have a much higher risk score for these features compared to legitimate users, and low RSR means there isn't much difference in the risk score between attackers and legitimate users for these features. So higher RSR value is better. And there is a server-side features, right? So the features we can get from server-side, which is basically it is generated by the server, which is because it is generated by the server, these feature value are hard to spoof. In this example, let's just explore this graph, okay, this table. Okay, the first feature is IP address. It's mentioned that if we just want to use single features for the applications, we can just use IP address. And there is also a major add-ons features that we can add to improve the accuracy if we want to use, which is there is an RTT, which is round trip time, rounded to 10 millisecond, 5 millisecond, ASN for the IP address, so we can determine the company or the ISP that owns the IP address, RTT in milliseconds, hour, login time, region based on the IP, weekday and hour of login. And there is a column JavaScript not required. So this is to show you that because in web applications users can turn off the JavaScript, right? So if they turn off the JavaScript, we cannot get the RTT because it requires a WebSocket communications. But anything else can be provided without JavaScript. And there is an RSR column, right? As we have discussed before, it means the difference in risk score between legitimate and attacker logins. High score means attacker have much higher risk score. Less score means not much difference. So you can see here, IP address. IP address has a good RSR score, but the best one here is round trip time 10 milliseconds. That can clearly differentiate between high attacker and legitimate users. So probably I will create a separated video talking about using RTT for the risk features in the separated video. And the next two columns is H global and H user. This is the entropy of the global and users, right? So if the H global value is high and then the H user is low, means that the features are different across all users and changing rarely for individual users, right? So that's why for IP address, the value of H user is considered to be low compared to be low, or yeah, not really low, but yeah, it's okay. Like individual user change it rarely, right? And also the global value is very high, so it means that the value is different across all users. Okay, there is an ambulance. Alright, sorry for the noise of the ambulance, right? And then you can see again, for example, RTT 10 milliseconds, the H user is quite low, but the lowest is region, but it's rarely changed for individual users, and that's, yeah, makes sense because I think users rarely travel to different regions in this example. Okay, the next column is unique values. It's mapped with 5-dot scale, very low, low, medium, very high, high and very high, mapped to these values. So if the unique values is low, means that it's not that unique, right? You can see that IP address is very unique, so it's very useful to distinguish legitimate logins from suspicious ones. But like our regions, it's less unique between attackers and suspicious legitimate users, right? And last column is median logins until re-authentications. It tells us how many times legitimate users can log in before being asked to re-authenticate, right? So high value means less frequent interruptions. Less value, small value, means more frequent re-authentications prompts. So which R is highest here, like hour and weekday and hour, right? But the lowest is, I think, RTT 10 milliseconds, right? It's more frequent re-authentications prompt. Yeah, so this is the server-side features based on the research paper tests. It gives us very good, let's say, informations. So we can have based on what server-side features we can choose. And the next type of features is client-side features, which is easier to be spoofed. This is some of the example. This is not the whole data, but you can see I think one of the good features that we can use from client side is like session cookie. Why? Because the RSR value is very high, unique value is high, median login authentication is very high, and also like user agents also is very good features that we can use from client side. So let's summarize what we have learned so far. So using MFA can improve security, however need to be find a balance between security and usability. Therefore we can use RBA, which just can improve security without adding additional authentication steps. And it turns out that login history size impacts the RBA model performance. And then choosing RBA features is also important to choose it correctly. We should choose features that is hard to spoof, and we have to choose features that can distinguish between legitimate users and attackers. So that's all of the informations that I want to share with you in this video. I hope you enjoy and like it. Until the next video, stay healthy and keep learning. Bye bye.